All right, hey everyone. Okay, I guess we're live. As Artie was saying, please enter your Sonnet ID. We can bring this up again at the end of class today. We'll just take another 20 seconds, and then we'll go on to the main discussion. Right. All right. So what I want to discuss with you today is maybe what I'm going to call full cycle deep learning applications, right? And so I think this Sunday, you'll be submitting your proposals for the class projects you do this quarter. And in most of the, in a lot of what you learn about in machine learning projects, you learn how to build machine learning models. What I want to do today is share with you the bigger context of how a machine learning model, how a neural network you might train, fits in the context of a bigger project. So what are all the steps, right? Just as if you're writing a software product, you take other classes that learn you, what happened there? That teach you how to build a website, for example. Wow, what is that? But to build a product requires more than just building a website, right? So what are the other things you need to do to actually do a successful software project? In this case, to do a successful machine learning application. And so let's see. So yep. Oh, test. Is the audio on? Test. Could you turn up the audio? No. How's this? Nope. Can't hear me at all. Hi. Oh, I think I'm broadcasting. I hear myself great. All right. Okay, you can hear me now. Great. Thank you. All right. Thank you. All right. So what I want to do is share with you full cycle machine learning, not just how to, you learn a lot about how to build deep learning models, but how does that fit in a bigger project, right? Just as if you're taking a class on building a website, then great, you know how to code up a website, that's really valuable. But what are all the things you need to do to make a successful website or to build a project that involves launching a website or a mobile app or whatever? So as you plan for your class project proposals due this Sunday, if you're doing an application project that fits in the context of a bigger application, also keep some of these steps in mind, right? So, these are what I think of as the steps of an ML project, or really maybe not class project, but maybe a serious machine learning application, right? And I don't know, I've built a lot of machine learning products over several years. So some of these are also things that I wish I had known, many years ago. This one's maybe kind of obvious, but select a problem. And let's say for the sake of simplicity that you use supervised learning, right? It turns out for the CS230 class projects, I think more than 50% of the class projects tend to use supervised learning. There are also other projects that end up using GANs, which we'll talk about later this quarter, or other things. But I think, let's say you use supervised learning to build an interesting application. And I think for today, I'm going to use as a running example building a voice-activated device, right? So, I don't know. Actually, how many of you have a smart speaker in your home, like a voice-activated device in your home? In the U.S., wow, not that many of you. Interesting. Okay, cool. Yeah. So I think the Amazon Echoes, Google Homes, the Apple Series, or in China, one of my former teams built Baidu DuerOS. But let's say, for the sake of argument, that you want to build a voice-activated device, and I'm going to use this as a running example. And so, in order to build a voice-activated device, and again, I'm not going to use any of the commercial brands like Alexa or OK Google or Hey Siri, or I guess in China it was Hello Xiaodu or Xiaodu Ni Hao, which means kind of roughly Hello Little Du. But let's use a more neutral word, which is let's say you wanted to build a device that responds to the word activate. And you're actually going to implement this as a problem set later this quarter. But so you want to build a, yeah. Okay, no, volume up. Let's see, how do I, okay, is this better? No? Yes? No? This is better? Okay, cool, thank you. A little bit ironic, talking about speech recognition and the volume isn't high enough. Okay. So let's say you want, wow, let me know if I've come soft again, but thank you. Yeah. So let's say you want to build a voice-activated device. So the key components, the key machine learning, deep learning component is going to be a learning algorithm that takes as input an audio clip and outputs, did it detect what's sometimes called the trigger word. No. Did I go soft again? Okay, this is okay. Right. All right. And outputs Y, 0, 1. Did you detect the trigger word, such as Alexa or OK Google or Hey Siri or Hello Little Do or Activate or whatever wake word or trigger word, right? And so step 1 is select a problem, and then in order to train a learning algorithm, you need to get labeled data if you're applying supervised learning. And then you design a model, right? Use backprop or some of the other algorithms you learn about, momentum, Atom, various optimization algorithms, gradient descent, to train the model. And then maybe you test it on your test set. And then you deploy it, meaning you start selling these smart speakers and putting them hopefully into your users' homes. And then you have to maintain the system. And I'll talk about this later as well. And this is not chronological, but one thing that's often done, but I want to talk about it at the end instead, is not really step 8, is QA, which is quality assurance, which is an ongoing process, right? And so let's see. So if you want to build a product, if you want to sell a machine learning product, these are maybe some of the key steps you need to work on. Some observations. When you train a model, training a model is often a very iterative process. So every time you train a machine learning model, you find that, I can almost guarantee whatever you do, it will not work, at least not the first time. Right? And so you find that even though I've written this as a sequence of steps, when you train a model, you're going to go, no, that neural network architecture didn't work. I need to increase the number of hidden units or change the regularization or switch their RNN or switch to a totally different architecture. And sometimes you train a model and go, nope, that didn't work. I need to get more data, right? And so this is often a very iterative process where you're cycling through the several different steps here. And then I think one distinction that you have not yet learned about in the Coursera, in the Deep Learning.ai Coursera videos is how to split up the data into train, def, and test. So I'm going to simplify those details for now, but just as a foreshadowing, I guess, of what you learn later in the Deep Learning.ai Coursera videos is how to take a data set you have, train into a training set, into a set that you actually test, cross-validate doing development, called a dev set or development set or holdout cross-validation set, as well as a separate test set. So you learn about this later, but I'm just simplifying a little bit for today. Okay, so I think the first thing I want to do is ask you a question, right? So we're going to talk through many of these steps. Oh, and it turns out that what a lot of machine learning classes do, and do a good job teaching, is focusing on maybe these 3 steps or maybe these 4 steps, right? And what I want to do today is spend more time. So this is the heart of machine learning. How do you build a great model? And what I want to do today is spend more time talking about step 1, and 6 and 7, and just a little bit of time talking about the core of this, because you kind of need to do the other steps well as well if you want to build a deep learning product or build a machine learning application. Okay, so let's start with a discussion question. I'm actually curious if you're selecting a project to work on. what are the, actually, so I don't answer this yet. I'll tell you what the question I'm going to ask is, which is, all right, what properties make for a good candidate deep learning project? Don't answer yet, right? I want to say a few more things before I invite you to answer, which is that all of you for the last few days, I hope, have been thinking about what project you want to do for this class. And what I want to do is just discuss some properties of what are good projects to work on and what are maybe not good projects to work on. Okay, and think of this as your chance to give your classmates advice, right? What are the things your classmates should think about? They're trying to decide this is a good project to work on. Okay, and so what I want to do for today is use this voice-activated thing as a motivating example. And you know, there's actually one project I was working on. Actually, there was one project I thought of working on, but decided not to work on, and there's a voice-activated device. So it turns out that these voice-activated devices, like Echo, Google Homes, and so on, they are taking off quite rapidly in the US and around the world. It turns out that one of the significant pain points of these devices is the need to configure it, right, to set it up for Wi-Fi. So I've done a lot of work on speech recognition, helped out, did a lot of work in Google Speech System. I led the Baidu Speech System. So I've been published papers on speech recognition, and I have one of these devices in my home. Right? Actually, I have an Amazon Echo in my living room. But even to this day, I have configured exactly one light bulb to be hooked up, to be controlled by my Echo, because the setup process, not blaming any company, is just difficult to hook up, a Wi-Fi enabled light bulb, and then to set it up so that your smart speaker or whatever, as you can say, smart device, turn off the lamp. So I have one light bulb in my living room, right, that I can turn on and off, and that's it, right? Even as a speech researcher. So, maybe I'll say a bad example. So one application that I think that I was actually seriously considering working on is to build a embedded device that you can sell to lamp makers, so that, I don't know where you buy your lamps from, but I have a few lamps from IKEA or a few lamps from wherever. But you can buy a desk lamp, so that when you buy the desk lamp, there's already a built-in microphone, so that without needing to connect this thing to Wi-Fi, it's like, hey, here's a $20 desk lamp, put it on your desk, and you can go home and say, desk lamp turn on, or desk lamp turn off. Then I think that will help a lot more users get voice-activated devices into their home. And it's actually not clear to me, if you want to turn on a desk lamp, it's actually not clear to me that you want to turn to a smart speaker and say, hey, smart speaker, please turn on that lamp over there, right? Maybe it feels more natural to just talk directly to a desk lamp and tell it to turn on and turn on. And so, also for what it's worth, some of my friends and I, we evaluated this. We actually thought that this could be a reasonable business to build embedded devices to sell to lamp makers or other device makers, so that they can sell their own voice-activated devices without needing this complicated Wi-Fi setup process. And so to do this, you would need to build a learning algorithm and have it run on an embedded device that just inputs an audio clip and outputs, whenever it detects the wake word. And instead of a wake word being activate, the wake word would be a lamp turn on or lamp turn off. You need two wake words or trigger words, one to turn it on, one to turn it off, right? Oh, and I think just the other thing that I think would make this work is to give these devices names. So if you have 5 lamps or 2 lamps, you need a way to index into these different desk lamps. So let's say you decide for your project, to have a little switch here. So this lamp could be called John or Mary or Bob or Alice, like a 4-way switch. So that depending on where you set this 4-way switch, you can say, John, right, turn on, right? Or if you decide to call this lamp John, I also give it some other name, so you don't have every lamp by the same name, okay? So what I'm going to do is use as a motivating example this as a possible project. Oh, and I'm not working on this. If any of you want to build a startup doing this, go for it. This is not, I felt my teams and I had better ideas, so we want to do other things in this, but I actually don't see anything wrong with this. I think this actually could be a reasonable thing to pursue as well, but I'm not doing it, so you're very welcome to if you want, okay? So Now the question I want to pose to you is, when you're brainstorming project ideas, like this idea, some other idea, what are the things you would want to watch out for? What are the properties that you would want to be true in order for you to feel good proposing this as a CS230 project, right? So why don't you take a minute and write this down? I think, yeah, if you're asking a friend, if a friend is asking you, what are the things I should look at to see if something is a good project, what would you recommend to them? So feel free, just write down a few keywords and then we'll see what people say. And then I'll tell you what I tend to look out for when I'm selecting projects. And I have a list of 5 points. Why don't you take I don't know, 2 minutes to...
It's not activated. Yeah.
Oh, sorry, this is not activated? You're not able to enter answers, okay. Let me test the internet access. Just checking. Yep, I am connected to the internet. RT, any ideas? Oh, I see. Okay. All right, let me try that. Oops. Oh, it's working now? Okay, thank you.
Turn off the... It keeps turning off.
Oh, yes, thank you. Yeah, thanks. So can you take 2 minutes to enter? And I think I configured this to let you enter multiple answers. Let me just take 2 minutes. All right, another 1 minute. All right, 30 seconds. Okay, 3, 2, 1. Well, maybe in hindsight, that wasn't the best visualization. Can people see this? Well, never mind. Trying to see if, all right, so data, novelty, lots of data. Some of these are really small. Human doable, number of examples, doable in 2 months, no office algorithm, new industry or field, clear objective, practical, useful. Huh. Oh, can we finish in time? Host real life problem, useful hasn't been done, computationally tractable. Yeah, generalization. I see, cool, great. Let me make some comments on these. I think this is pretty good. I had a list of 5 bullet points that maybe I just share with you my list of 5, which is I think just some things I encourage you to pay attention to. You know, this may or may not be the best criteria, but interest, I think interest just hopefully you can work on something that you're actually interested in. And then I think right, data availability, which many of you cited, is a good criteria. One of the ways that Stanford class projects sometimes do not go well is if students spend a month to try to collect data, and after a month have not yet found the data, and then you know, and there's a lot of wasted time. One thing that I would encourage you to consider as well is domain knowledge. And I think that if you are a biologist and have unique knowledge into some aspect of biology to which you want to apply machine learning, that will actually let you do a very interesting project, right? That is actually difficult for others to do. And I think more generally, as advice for navigating your careers, right? So, you know, it's interesting because AI, machine learning, deep learning, there's so many people wanting to jump into machine learning and deep learning. Actually, I'll give you an example. So I sometimes talk to doctors, you know, radiology students, including like Stanford and other universities' radiology students that want to learn about machine learning, right? Because they hear about deep learning maybe someday affecting radiologists' jobs, and so they want to be part of deep learning. And so my career advice to them is usually to not forget everything they learned as a doctor and try to do machine learning 101 from scratch and just forget everything they learned as a doctor and just become a CS major. I think that path can work, but I think where a radiologist could do the most unique work that allows them to make the most unique contribution is that they use their domain knowledge of healthcare and radiology and do something in machine learning applied to radiology, right? And so, all right, how many millennials are there in this class? Okay. What is that me thing? All right. All right. This is really wrong. Yeah, I think it's because of the word cloud. So everybody counts word frequency, right? The money thing, I don't know. I have very mixed feelings about that. Yeah. All right, but I think actually I actually know that some of you are taking deep learning because you work in a different discipline and you want to do something in this hot new exciting thing of machine learning. And I think whatever discipline you're in, if you have domain knowledge about some other area, education, civil engineering, biology, law, taking deep learning allows you to do very unique work applying machine learning to your domain, right? Let's see. I think that. I think, well, I call it utility, but several of you mentioned as well, something that has a positive impact that actually helps other people. And I don't know, money could be an aspect of utility, but maybe not the most inspiring one. And then I think, and I think one of the biggest challenges we face in the industry today is still, frankly, is actually good judgment on feasibility. So today, I still see too many leaders, sometimes CEOs of large companies, that stand on stage and announce to the whole world, we're going to do this machine learning project to do this by this deadline. And then 20 minutes later, I talk to their engineers, and the engineers say, no, there's no way, not happening. What the CEO just put on stage, whole engineering organization is not doing it and knows it's impossible. So I think one of the biggest challenges is actually feasibility. And in fact, I actually know that, I was chatting with RT about the TA office hours, and I know that there have been a lot of you have been thinking about applying end-to-end deep learning, right? Can you input any X and output any Y and do that accurately? And sometimes it's possible and sometimes it's not, and it still takes relatively deep judgment about what neural networks can and cannot do. with a certain amount of data that you may or may not be able to acquire in order to do some of these things, right? So I think throughout this quarter, you gain much deeper judgment as well on what is feasible, I guess. It was pretty interesting. I once I knew a CEO of a large company that once told his team, he actually gave his team these instructions. He said, I want you to assume that AI can do anything. I think that had an interesting effect, I guess. Yeah, cool. All right, so I think step one was select a project. I hope there's existing projects, try to keep some of those things in mind. Step two is get data, right? And so what I want you to do, and I'm going to pose a second question and then have some of you discuss, is let's say that you're actually working on this, smart voice-activated embedded device thing, right? So let's say that you and your friends want to build a startup to train a deep learning algorithm to detect, phrases like John turn on or Mary turn off or Bob turn off or whatever to sell to device makers so that they can have a little embedded voice detection chip that doesn't require a complicated Wi-Fi setup process, right? So let's say you actually want to do this. So you need to collect some data in order to start training a learning algorithm, right? So the second question I'll pose to you is a question in two parts, but I'll have you answer it all at the same time, which is in how many days, let's say you actually propose this for your CS230 project this Sunday, and then you start work on it, like on Monday, or you can start work on it today before the proposal. But how many days would you spend collecting data, and how would you collect the data? Okay, and I think, actually, how many of you have participated in engineering Scrum, if you know what that means? Oh, okay, a few of you. Oh, those of you in the industry. Okay, all right. So in engineering estimation, when you estimate how long a project takes, one of the common practices is use a Fibonacci sequence to estimate how long a project will take, right? And so Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, and so on. And it's roughly powers of 2, but doesn't grow as fast as powers of 2. And Fibonacci numbers are cool, right? But so what I want you to do, actually, let me just make sure I have the configuration right. What I would, speech bubbles. Okay, yeah, that's good. All right, so what I'd like you to do is in the text answer, really write two things. One is write a number. How many days do you think you spend on collecting data? You and your teammates, if you're actually doing this project. And then how would you go about collecting the data? Okay. So why don't you take like another 2 minutes to write in an answer. Oh, I'm sorry. Oh, let's hit reload. No, still not activated. Sorry about that, I'm trying to hit. Oh, interesting. That is not helpful. All right, that is definitely not helpful. All right, let's do this. Write down your answer on a piece of paper first and take 2 minutes to do that. So the two questions are how many days? Pick a number from a Fibonacci sequence. And, oh, are you able to use the RT? Oh, okay, let's swap out my computer for RT's. Oh, actually, yeah, oh, if RT's computer is working, actually, go ahead.
Oh, sorry. Oh yeah, I can just present.
Yeah, let's plug in your laptop, shall we? And just use your laptop. Is he sure? Yeah. That's interesting. I wonder if it's a network problem or a web browser problem. I started using Firefox recently in addition to Chrome and Safari, and that was Firefox. I'll try it with other web browsers later. right, cool. Okay, great. Thank you. Thanks, Archie. All right, maybe people that take another minute from now, just extend the time a bit to answer. All right, another 10 seconds. All right, cool. Let's see, I'm gonna show people's answers, okay? All right, well, 365. So there's a lot of variance in the answers, right? I don't know. Download from online depends on what data you want. It turns out, well, so if you're trying to find data, phrases like John turn on, that data doesn't exist online. It turns out that you're trying to find audio clips of the word activate. There are some websites with single words pronounced, but not a lot of audio clips actually. So the trigger word or the wake word is the word activate. There are some websites we can download like maybe 10 audio clips of a few people saying activate, but it's quite hard to find hundreds of examples of different people saying the word activate. 5 days it falls in the sky. All right, so let me suggest that you guys discuss with each other in small groups what you think would be the best strategy. How many days would you find collecting the data and how would you start collecting the data, and try to convince people next to you on that. And before I ask you to start discussing, I want to leave you with one thought, which is how long do you think it'll take you to train your first model, right? And so if it'll take you a day to train your first model or 2 days, do you want to spend X time collecting data and then spend, let's say, I don't know, to set up a deep learning thing and train a model, it might take a couple of days, right? Especially if you download open source packages. So if the amount of time needed to collect data is X followed by 2 days to train your first model, what do you think X should be, the amount of time? Why don't you guys spend like 2 minutes to discuss with each other and see if you can their answers are, there's very large variance, right? Why don't you guys discuss? If you actually, if the people sitting next to you are your project partners, why don't you discuss with them how many days you think you should spend collecting data and how you collect the data? Okay, why don't you take 2 minutes to discuss and we can see what we do. All right. Oh. All right, guys. So, wow. All right, guys. Hey, guys. So, all right. A lot of exciting discussion. So actually, how many of the groups wound up on the low end? How many of you, convince each other that maybe it should be like 3 days or less? Oh, just a few of you. How come? Someone say why? Why is it why?
Because you want to just see if the algorithm works first. So you need some data to just test to see if your algorithm is even reaching some sort of good benchmark before you then go and collect a massive data set.
Cool, yeah, right. It gets a little bit of data to test how the algorithm works before you even go and collect a massive data set, right? Cool, yeah. And did anyone had a high end, like a 13 days or more? Very few? How come? Anyone with insights you want to share with the whole class, actually? What were you all discussing so excitedly? Oh, go ahead.
Depending on your domain knowledge, data collection can take a long time, especially for this problem. Based on one idea which we discussed in previous class, we were thinking you could use movie clips and subtitles to generate some audio signatures for the keywords which you want to trigger our system with, and that would take time to mine data from movies. So that could take depending on your domain knowledge, could take weeks.
Yeah, right, yeah. So the complicated systems to look at subtitled videos, right? YouTube videos with captions or something, and if there's appropriately Creative Commons data there, you could use, yeah. So let me tell you my bias. I'll just tell you what I would do if I was working on this project. Well, actually, with one caveat, if I haven't done so much work in speech recognition previously, right, but this was my first project, I would probably spend 1 to 2 days collecting data, kind of on the short end, right? And I think that, one of the reasons is that machine learning, kind of that circle I drew up there, is actually a very iterative process where until you try it, you almost never know what's actually going to be hard about the problem, right? And so, so if I was doing this project, I'll just tell you honestly what I would do. Again, I've actually thought about this project a bunch, right? Including trying to validate market acceptance and so on. But which is that I would get a cheap microphone, use a built-in laptop microphone, or buy a microphone off Amazon or something, and go around Stanford campus or go to your friends and have them just say, hey, do you mind saying into this microphone the word activate or John turn on or whatever, and collect a bunch of data that way. And then, and with 1 or 2 days, you should be able to collect at least hundreds of examples, and that might be enough of a data set to start training a rudimentary learning algorithm to get going. Because if you have not yet worked on this problem before, it turns out to be very difficult to know what's going to be hard about the problem. So is what's going to be hard highly accented speakers, right? Or is what's going to be hard background noise? Or is what's going to be hard, confusing turn on with turn off? You hear John turn and then blah, blah, blah. But when you build a new machine learning system, it's very difficult to know what's hard and what's easy about the problem. Or what's going to be difficult, that far field, which is the technical term for if the microphone is very far away, right? So it turns out that if we turn on the microphone on my laptop now, for example, the laptop, which is like 3 meters away from me, will be hearing voice directly from my mouth, as well as voice bouncing off the walls. So there's a lot of reverberation in this room, and so that makes speech recognition harder. Human ear is so good at processing out reverberant sounds, reverberations, that you almost don't notice it, but the learning algorithm will sometimes has problems with reverberations, right, or echoes bouncing off the hard walls of this room. And so depending on what your learning algorithm has trouble with, you will then want to go back to collect very different types of data or explore very different types of algorithms. Or it's a problem that sometimes it's because it's just the volume is just too soft, in which case, maybe you need to do something else to normalize audio volumes or buy a more sensitive microphone or something. So it turns out that when building most machine learning applications, unless you've experienced working on it, so I've actually worked on this problem before, so I have a sense of what's hard and what's easy, but I work on a new project for the first time. It's very difficult to know what's hard and what's easy. And so my advice to most teams is rather than spending, say, 20 days to collect data, and then 2 days to train a model, and it's often by training a model and then seeing what are the examples it gets wrong, when does the algorithm fail, that lets you feedback to either collect more data or redesign the model, right, or try something else. And if you can shrink the data collection period down to be more comparable to how long you end up taking to train your model, then you can start iterating much more rapidly on actually improving your model, right? Oh, and so maybe one rule of thumb I actually tend to recommend for most class projects is, I don't know, maybe if you need to spend up to a week to collect data, maybe that's okay, but you can get going even more quickly. I would even maybe more strongly recommend that. And there have been so few examples in my life where the first time I trained a learning algorithm, it worked, right? It like pretty much never happens. It happened once about a year ago, and I was so surprised I still remember that one time, right? And so machine learning development is often a very iterative process, and by quickly collecting data set, and often data sets are collected through sweat and hard work, right? And so I would literally, and actually, I've actually done a lot of speech, and to get going quickly, I would probably just have myself or my team members run around and find people and ask them to speak into a microphone and record audio clips that way. And then only when you validate that you need a bigger data set would you go to more complicated things like set up an Amazon Mechanical Turk thing, right, to crowdsource, which I've also done, actually. I've also had very large data sets collected off Amazon Mechanical Turk, but only in the later stage of the project where you understand what you really need, right? So as you start work on your class projects, maybe keep that in mind. So, now, oh, so one other tip that machine learning researchers, on average, we tend to be terrible at this, but I'll give this advice anyway, is when you're going through this process, get some data, design a model, a literature search would be very helpful. So see what algorithms others are using for this problem. It turns out the literature is actually quite immature. There isn't a convergence of like a well-standard set of standard algorithms for trigger word detection in the literature right now. Actually, people are still making up algorithms. So if you do a literature survey, you find that to be the case, but you need to train an initial model. And in most machine learning applications, you go through this process multiple times. So one tip that I would recommend you do is keep clear notes on the experiments you've run. Right? Because it'll often be, as you train a model, you say, oh, this model works great on American accented speakers, but not on British accented speakers. Right? I was born in the UK, so I'm just going to use British accents for an example. If you're from a different part of the world, you can think of different global accents, but since I'm from the UK, I'm just going to pick on British accents, I guess. Keep clear notes on the experiments run, because what happens in every machine learning project is after a while you have trained 30 models, and then you and your team members are going, oh yeah, we tried that idea 2 weeks ago, did it work? And if you have clear notes from when you actually did that work 2 weeks ago, then you can refer back rather than have to rerun an experiment. The other thing that some groups do is have a spreadsheet that keeps track of what's the learning rate you use, what's the number of hidden units, what's this, or keep it in a text document so that which will make it easier to refer back to notes on what you tried earlier. This is one piece of commonly given advice. This is one of those things that every machine learning person knows we should do this, but on average, we're very bad at doing this. But you could, I don't know. Yeah. But at the times I managed to keep good notes, it actually saved a lot of time, right, to try to remember what exactly you tried 2 weeks ago. Okay? So a lot of this class will be on this process of how to get data, develop the train, dev, test, split, design the model, train the model, eventually test the model and iterate. Okay, so a lot of this class is on this. So I want to jump ahead to when you have a good enough model and you want to deploy it. Okay, so step 6, I guess, is deployment. Now, this is one of the reasons I want to step through this example, going through a concrete example, is I find that when you're learning about machine learning for the first time, is often seeing, what my team tends to call war stories, kind of stories of projects that others have built before that often provides the best learning experience. So I think like I have built speech recognition systems. It took me like a year or 2 years or something to do it. So I'm trying to, so rather than, having you spend 2 years of your life building speech systems, if I can summarize a war story, right, to tell you what the process is like, I'm hoping that these concrete examples of what building these systems are like in, large corporations, that can help you accelerate your learnings without needing to get 2 years of on-the-job experience. You can just hear the salient points. Okay. Now, if you're deploying a system like this, one of the things, and this is actually true, this is actually a real phenomenon for deploying speech systems, is you have the audio clip, you have a neural network, and then, this will output 0, 1. And the neural networks that work well will tend to be relatively large, right? Relatively large model, large number of hidden units, relatively high complexity. And if you have some of the smart speakers in your home, you recognize that a lot of them are edge devices as opposed to purely cloud computation, right? So we all know what the cloud is and what an edge device is. An edge device is a smart speaker that's in your home or the cell phone in your wallet. So edge devices are the things that are close to the data as opposed to the cloud, which is a giant service we have in our data centers, right? So because of network latency and because of privacy, a lot of these computations are done on edge devices, like a smart speaker in your home, or I guess, Hey Siri or OK Google can wake up your cell phone, right? And so edge devices have much lower computational budgets and much lower power budgets, limited battery life, much less powerful processors than we have in our cloud data centers. And so it turns out that serving up a very large neural network is quite difficult, right? It's very difficult for a low power, inexpensive microprocessor sitting on a smart speaker in your living room to run a very large neural network with a lot of hidden units and a lot of parameters. And so what is often done is to actually do this. Which is to input an audio clip and then have a much simpler algorithm figure out if anyone is even talking, right? Because so the smart speaker, in my living room hears silence most of the day, right? Because usually just no one at home, right? There's no voice, and then only if it hears someone talking, then feed it to the big neural network that you've trained and ramp up, use a larger power budget in order to classify 0, 1. Okay? This component goes by many different names in reasonably standard terminology, but not totally standard terminology. In the literature, I'm going to call this VAD for voice activity detection. Right? It turns out that voice activity detection is a standard component in many different speech recognition systems. If you are using a cell phone, for example, VAD is a component that tries to figure out if anyone's even talking, because if it thinks no one is talking, then there's no need to encode the audio and try to transmit the audio, right? Yeah, Aarti, could you? Yeah. No? Yeah. And so, so the next question I want to ask you, and I thought this was timely because, is a couple options, right? Option one is to build a non-machine learning based VAD system, voice activity detection system, which is just, see if the volume of the audio your smart speaker is recording is greater than epsilon. So if there's silence, just forget it. And option 2 is train a small neural network to recognize on human speech. Right? And so my next question to you is, if you're working on this project, would you pick option 1 or would you pick option 2? Right? As you move toward. Oh, sorry. And I think a small neural network. A small neural network, or in some cases, I've seen people use a small support vector machine as well. For those of you who know what that is, a small model can be run with a low computational budget. It's a much simpler problem to detect if someone is talking than to recognize the word that's said. So you can actually do this, with reasonable accuracy with a small neural network. But if you're actually working on this project for CS230, which would you try first? Right? So actually, could we come to the next question?
Yes.
Okay,
Sorry,
cool.
I can't figure out how to do that.
Oh, sure.
I'll
Yeah,
just
yeah.
keep it
We can let them start answering, I guess, and
Okay.
then while you figure out the projection. Cool.
I'll just keep unlocking it periodically.
Are people able to vote? No, there are no votes yet. Whoa,
I have weird shortcuts.
I see. I guess you write so much code, you have a shortcut to go to your coding environment on your laptop.
Great. Does that work?
All right, cool. Great, thank you.
Sorry about all of this.
Oh, wow, great. All right. People answering quickly. Another 20 seconds, if that's enough time to get any answers. All right, cool. That's fascinating. There's a lot of disagreement in this class. People want to say why? Why would you choose option 1? Why would you choose option 2? And I have a very strong point of view on what I would do, right? But I'm curious why option 1 and why option 2? Go ahead. Okay, easier to debug the language issues. Anyone else? Either arguments for option 1 or option 2. If you go ahead.
Option 1 is simple.
Option 1 is simple. Anyone else?
Option 2 is not that hard either.
Oh, option 2 is not that hard either.
Well, I was thinking option 1, if you have a dog in your house and barks, it's probably going to activate it. So when you implement option 2, you can probably kind of already simplify the problem by taking some of the noise that's not, it's a noise, activates the machine, but it's still a noise. So that's why I picked option 2.
Yeah, right. If a dog barking, option 2 would be much better at getting rid of.
Yeah, some kind of those noise.
Cool. All right. Just two of you in blue. Go ahead.
Option 2, there may be noise. People have sleep whispering. So
What if someone's whispering? Right. What if someone's
I
whispering?
vote for non-ML because for option 2, maybe you're in a very noisy place. Okay, never mind.
Yeah.
And
Yeah, cool.
you're in a very noisy place. Option 2, I think it will pick up the background noise.
Yeah, cool. Yeah, right. If you're in a noisy place, I have a friend who's lives next to a train station, and so right. So option one would pick up a lot of training. Which is the last one? Go ahead.
Whichever option you pick has to be running constantly. So you want something that's very cheap. So it seems like option one is better because it would be very cheap for your system to run that.
Oh yeah, whatever you pick has to be running constantly, so you want to be cheap, right? Low power, low compute. So let me just share with you some of the pros and cons. I think there are pros and cons to option one and option two, which is why there's so many votes for both options. I personally would choose option one, but let's just discuss the pros and cons, right? I think that option one. First is just a few lines of code. Yes, maybe option two isn't that complicated, but option one is even simpler. And I think that, actually, maybe I would say if I hadn't worked on this problem before, I would choose option one. But since I have experience in speech recognition, eventually I know you need option two, but that's because I've worked on this problem before. But if it's your first time working on a speech application problem, I would encourage you, on average, to try the really simple, quick and dirty solutions and go ahead and, so let's see, how long would it take you to implement this, right? I would say like 10 minutes, 5 minutes, I don't know, right? How long would it take you to implement that? I don't know, like what, 4 hours, 1 day? I don't really know actually, right? Let me just write 1 day, I'm not quite sure, right? But if option one can be implemented in 10 minutes, then I would encourage you to do that and go ahead and put the smart speaker in your home or in your potential users' homes. And only when you find out that the dog barking is a problem or the train on the railway station or whatever is a problem, then go back and invest more in fixing it, right? And in fact, it's true that maybe it's annoying if the dog barking keeps on waking up the system, but maybe that's okay, because if the large neural network then screens out all the dog barking, then the overall performance system is actually just fine. And you now have a much simpler system, right? But it turns out that the reason you might need to go to option two eventually is because there are some homes in noisy environments, there's constant background noise, and so that will keep the large neural network running a little bit too frequently. So if you have a large engineering budget, so some of the smart speaker teams are like hundreds of engineers working on it. So you have hundreds of engineers working on it, totally, option two will perform better. But if you're a scrappy startup team with 3 of you working on a class project, the evidence that you need that level of complexity is not that high. And I would really do that first and use that to gather evidence that you really should make the investment to build a more complex system before actually making the investments of days and eventually, I think this is 1 day to build your first prototype, right? And then eventually it'll be more complicated. It turns out that the other reason, the other huge advantage of the simple method is the following. And this is one of the, frankly, this is actually one of the big problems and big weaknesses of machine learning algorithms and deep learning algorithms, which is what happens is when you build a system and you ship a product, the data will change, right? And so I'm going to simplify the example a little bit, but I know Stanford is very cosmopolitan. This Palo Alto is very cosmopolitan. So if you collect data in this region, you get accents from people all over the world, right? Because that's Stanford or that's Palo Alto. But just to simplify the example a little bit, let's say that you train on U.S. accents, right? But for some reason, when you ship a product, maybe it sells really well in the UK, and you start getting data with UK or with British accents, right? So one of the biggest problems you face in practical deployment of machine learning systems is that the data you train on is not going to be the data you need to perform well on. And I'm going to share with you some practical ideas for how to solve this, but this is one of those practical realities and practical weaknesses of machine learning that is actually not talked about much in academia, because it turns out that the data sets we have in academia are not set up well for researchers to study and publish papers on this. I think we can set up new machine learning benchmarks in the future. But this is one of those problems that is actually kind of underappreciated in academic literature. but that is a problem facing many, many practical deployments of machine learning algorithms. And so more generally, the problem is one of data changing, right? And you might have new classes of users with new accents, or you might train a lot on maybe you get data from even Stanford users, and maybe Stanford is not too noisy, or Stanford has certain types of characteristics. When you ship it to another city, another country that's much more noisy, different background noise. Right? Or you start manufacturing the smart speaker, and to lower the cost of the speaker, they swap it out. They swap out the high-end microphone that you use from your laptop to collect the data for a lower-end microphone. Right? It's a very common thing done in done in manufacturing. Right? If you could use a cheaper microphone, why not? Right? And often to human ears, the sound sounds just fine on a cheaper microphone. But if you train your learning algorithm using your, I use a Mac, but a Mac is a pretty decent microphone. So if you train the data using audio collector from a Mac, and then eventually there's a different microphone, it may not generalize well. So one of the challenges of machine learning is that you often develop a system on one data set, and then when you ship a product, something about the world changes, and your system needs to perform on a very different type of data than what you had trained on. And so what will happen is, after you deploy the model, the world may change, and you'll often end up going back to get more data, redesign the model. Right, and I guess this is the maintenance of the machine learning model. I want to give some other examples. Web search, right? This happens all the time at multiple web search engines, which is you train a neural network or you train a system to give relevant web search results. But then something about the world changes. For example, there's a major political event, some new person is elected president of some foreign country, or there's a major scandal, or just the internet changes, right? Or there's actually what happens in China is that new words get invented all the time. I've worked at Google and Baidu, but the Chinese language is more fluid than the English language, and so new words get invented all the time. And so the language changes, and so whatever you train just isn't working as well as it used to, right? Or maybe a different company suddenly shuts off, their entire website to your search index because they don't want you indexing their website, and so the internet changes, and whatever you had done doesn't work anymore. Self-driving. Right? It turns out if you build a self-driving car in California, and then you try to deploy these vehicles in Texas, it turns out traffic lights in Texas look very different than traffic lights in California. So a model trained on California, Texas, so a neural network trained to recognize California traffic lights actually doesn't work very well on Texas traffic lights, right? I'm trying to remember which way around it is, but I think California and Texas has a different distribution of horizontal versus vertical traffic lights, for example, right? It's actually, humans don't notice, you go, oh yeah, red, yellow, green, but the learning algorithm doesn't actually generalize that well if you go to a different location. If you go to a foreign country, again, traffic lights, signage, the lane markings all change. Or I guess, one example I was working on earlier this week, right? Manufacturing, right? Landing AI, working on inspection of parts in factories. And so if you are doing visual inspection in a factory and the factory starts making a new component, they were making this model of cell phone, but cell phones turn over quickly, but in a few months later, they're making a different type of cell phone, or something weird happens in the manufacturing process. So the lighting changes, or there's a new type of defect. So the world changes, right? And should I lock again? What I'd like to do is actually revisit the previous question in light of this, the world changes phenomenon, right? Which is, let's say you've collected a lot of data with American accented speakers, and then, we ship the product to the UK, and then And then for some reason, you find that you have all these British accent speakers, right, trying to use your smart speaker. So between these two algorithms, the non-machine learning approach, which is just set the threshold, versus train a neural network, which system do you think will be more robust for VAD, voice activity detection? All right, take like another, I don't know, 40 seconds. All right. Yeah, interesting. Do people want to comment? Well, more people voted for non-ML. Does someone want to explain why? Yeah, go ahead.
What accents it only gets the twice. So using a non-ML would still be simpler than it used to for all other pros. If we want to detect the particular word and not just voice, then maybe we need NNs that do not just detect.
Yeah, cool. Yeah, right. So saying for the VAD voice activity detection, if you just measure the volume, then it doesn't really depend on the accent, right? So non-ML might be more robust. Anyone else? All right. So again, let me again share your thoughts. So it turns out that if you train a small neural network to American accented speech, there's a bigger chance that your neural network, because it's so clever, right, that it'll learn to recognize American speech and have a harder time generalizing to British accented speech. Does that make sense? And so one of the things that I've seen a lot of teams, so one way the non-ML thing could fail to generalize would be if British speakers are systematically, louder or softer than American speakers, right? So, I don't know. I don't know if Americans stereotypically are louder or less loud than British, but if American and British speakers, one country just has louder voices or softer voices, then maybe the threshold you set won't generalize well. But that seems unlikely, right? I don't see that being a realistic thing. But if you're training a neural network with a lot of parameters, then it's more likely that the neural network will pick up on some idiosyncrasy of American accents to decide if someone is even speaking, and thus may be less robust to generalizing into a British accented speech, right? And another way to think about this, if you imagine, to take an even further example, imagine that you're using VAD for a totally different language than English, right? Where take a different language, Chinese or Hindi or Spanish or something, where the sounds are really different. If you train a VAD system to detect, English, it may not at all work for detecting Spanish or Chinese or French or some other language. And so if you think of British accents as somewhere on the spectrum, not a foreign language by any means, but just more different, then I think the non-ML system is more likely to be robust, right? And so one of the lessons that a lot of machine learning teams learn the hard way is if you don't need to use a learning algorithm for something, if you can hand code a simple rule, like if volume greater than 0.01, do this or that, those rules can be more robust. And one of the reasons we use learning algorithms is when we can't hand code something, right? I don't know how to hand code something to detect a cat or detect a car on the road or detect a person. So use learning algorithms for those. But if there's actually a hand-coded rule that actually does pretty well, you find that it is more robust to shifts in the data and will often generalize better. Oh, and if any of you take we talk about this a little bit in CS230. I think CS230T talks about this as well, but this particular observation is backed up by very rigorous learning theory. And the learning theory is basically that the fewer parameters you have, if you still do well in your training set. If you can have a model with very few parameters that does well in your training set, you generalize better. Right? So there's very rigorous machine learning theory that basically says that. And in the case of the non-machine learning approach, there's maybe one parameter, which is what's the threshold for epsilon. And if that's worked well enough for your training set, then your odds of it generalizing, even when the data changes, is much higher. Right? Now, the last question I want to pose for discussion today is when discussing deployments, and so one of the lessons of deployment is that's just the way the world works. Build a machine learning system, deploy it, the world will usually change, and you often end up collecting data and having to iterate and maybe improve the model, right? And fix the model for British speakers or something. So we talked about edge deployments as well as cloud deployments, right? And so ignoring issues of user privacy and latency, which are super important, but for purposes of this question, let's put aside issues of user privacy and network latency. If you need to maintain the model, maintenance means updating the model, right? Even as the world changes. Oh, sorry, I mistyped. It should be, does a cloud or edge deployment make maintenance easier, not of, right? Why don't you just enter a one-word answer and why? Right, and so maintenance is when the world changes, something changes, so you need to update the learning model to take care of this British accent. So which type of deployment makes it easier? Let me just take another 2 minutes to enter your answers. All right, another 50 seconds. All right, cool. I'm gonna see what people wrote. Wow, cool, great. All right, almost everyone is saying cloud. Most people are saying cloud. Almost. All right, cool, great. And just to summarize, I think there are actually two reasons why most people say it's easier to push updates. That's part of it. I think the other part of it is that if all the data lives at the edge, if all the data is processed, in the user's home and none of it comes to cloud, then even if you have all these unhappy British accented users, you may not even find out, right? You're sitting in the company headquarters, you have all these users that mysteriously, seem to be not using your device, maybe because they're unsatisfied with it. But if the data isn't coming to your servers in the cloud, then you may not even find out about it. Now, there's serious issues about user privacy as well as security, right? So please, if you ever build a product, please be respectful of that and take care of that in a very thoughtful and respectful way of users. But so this is the cloud, right? If you have a lot of edge devices and all the data is processed there, you won't even know what your users are doing. And they're happy, unhappy, you just don't know. But if some of the data is streamed to your service at the cloud, and if the user privacy with really, please use good user consent, tell people what you're doing with the data. But if you take care of that in a reasonable and sound way, if you're able to examine some of the data, then you can at least figure out that, gee, it looks like analyzing the data, there are these people with this accent, this background noise that is giving a bad product experience. And you can also maybe have the data, so you can gather the data from the edge to feed back to your model, right? So it lets you detect that something's gone wrong. It lets you have the data to retrain the model to solve the British accent problem. You can retrain the model with a lot of British accent to speech. And then finally, it lets you push the model back out, right? So first, it lets you detect what's going on. Two, it gives you data for training. And three, it lets you more easily push the model back out, push the new model to production, to deployment, okay? And this is also why even if your computation needs to run on the edge, if you could, in a way respectful of user privacy and is transparent about how you use data, if you can get even a small sample of data or have a few volunteer users send you some data back to the cloud, that will greatly increase your ability to detect if something gone wrong, as well as maybe give you some data to retrain the model. So even if you can only do sort of push updates, right, this will help greatly, okay? All right, so finally, one last comment. I think one last challenge is in a lot of machine learning systems, you're not done at deployment. There's a constant ongoing maintenance process. And I think one of the processes AI teams are getting better at as well is setting up QA to make sure that when you update the model, you don't break something. So I think QA in large companies, quality assurance process, is kind of test this. And I think the way you test machine learning algorithms is different than the way you test traditional software, because the performance of machine learning algorithms is often measured in a statistical way, right? So it doesn't work and it doesn't work. It neither works nor doesn't work. Instead it works 95% of the time or something. And so a lot of companies are evolving the QA processes to have this type of statistical testing to make sure that even when you change the model and you do a push update, it still works 95 or 99% of the time or something. Rather, so putting in place new QA test processes as well. Okay. All right, hope that was helpful, stepping through what the full arc of a machine learning project will look like. We'll later this quarter, in course 3, as well as in a later lecture that I present, we'll keep talking about machine learning strategy and how to make decisions like this. So let's break for today.